Hey there, I'm Heather, and today we're going to talk about structural interpretation using seismic data. So this is a really fundamental skill in seismic interpretation and something that a lot of us do to better understand the geology that's been recorded in Earth's history beneath our feet. It's also very important if you're looking at structure to identify potential hydrocarbon traps. All right, so there's a couple of basics. I've already covered the theory behind reflection seismology in previous lessons. So now we're going to take it to kind of the next level and start doing it by marking seismic sections, not really marking them because this is a video, but one of the first things we want to do when we're looking at seismic is we want to kind of establish that geologic framework. And so this means going in and after doing some QC work, trying to identify the significant fault planes, perhaps important stratigraphic surfaces, understanding how the faults and horizons intersect with each other. And so you can think about this as building the skeleton of our interpretation. So when we talk about building a geologic framework, what we're really looking at is two main components, the structural interpretation and the stratigraphic interpretation. And so the structural side starts with trying to understand the faults, the folds, the areas where we may have subsidence and uplift, and the overall structural trends that are going on in the basin and at different points in time. And then the stratigraphic side focuses more on the unconformities, the stratal packages, different depositional environments, the relative ages of the rocks. And so the key that I've kind of stressed, hopefully, in previous lectures is that we want to try to use all of the available data. So from wells to seismic, outcrop studies, regional geology, and even if you got it, gravity and magnetic data. And so this is something that people often skip over. And what you want to do is you want to go out and you want to look and you want to understand the area you're working in before you start doing your seismic interpretation. Because what we want to make sure we do is that when we have our seismic interpretation, that it matches with all the other data that's out there, all the other knowledge that's out there, so that you have a really cohesive story about what's going on. All right, I forgot those were in there. Okay, so seismic interpretation plays several critical roles in structural analysis. So as I mentioned before, we're going to use it for faults, for folds. We're going to also need to make sure that when we map something in 3 dimensions, whether it's with 3D data or 2D data, that it geologically and geometrically makes sense. This is really important in terms of understanding the different timing relationships, particularly for trap formations. So the more accurate your data, your mapping is, the better hopefully you'll understand the uncertainties of the interpretation and what your seismic is able to tell you. So this goes back to the whole idea of understanding the reason you're mapping the seismic. Are you mapping it on a basin scale to understand the evolution of a hydrocarbon system? Or are you mapping it more on a very local scale where you're just trying to find another play or see if there's something of interest in a fault block nearby one you've already kind of worked on? So keep that in mind as you're kind of going through your interpretation. And interpreting data can take a lot of time. I know I've spent a lot of time listening to music and just mapping it. So it's not something we want to rush through because, we have all these tools that can help us auto pick, the horizons. We have a lot of AI tools and methods that can help us quickly map the faults, but there is actually some value in slowing down and really thinking about what you're seeing geologically. So don't rush through this process of interpreting and thinking of something that you just have to get through. Okay, so we've also talked already about how more advanced processing can dramatically help you improve your imaging, and that goes with structural imaging too. So if we look at these 3 versions of the same sections in the Rocky Mountain foothills, you can see how each step of processing, from time migration to pre-stack depth migration, and then even anisotropic, this is one of the words I've struggled with for like 20 years, pre-stack depth migration really reveals more detail about the thrust structure in this case. And so You want to keep in mind the type of data you're using, the type of acquisition, the type of processing that it's gone through. And if you have a case where you have a lot of uncertainty, you may want to see if it's worth it to try to reprocess the data to get more accurate results. Again, depending on the purpose you're interpreting seismic data. Okay, so I'm going to go through these really quickly from extensional settings, compressional, some strike slip examples, and some diapiric settings. And so just a quick review on faults, just a few basics. So just remember that faults represent the brittle deformation of rocks and are essentially planar discontinuities across which we see evidence of motion. So for normal faults, the hanging wall moves down relative to the footwall. In reverse fault, the hanging wall moves up. You may also, I also want to remind you of the key terms for throw for the vertical displacement and heave for the horizontal displacement. Another thing you want to keep in mind is that faults don't extend forever. They terminate both vertically and laterally, either at kind of like a tip point or where they intersect other faults. And so this is something to keep in mind, going back to the idea of seismic resolution, is that you may not be able to resolve exactly where that fault dies out just because of the seismic resolution of your data. So when we're interpreting faults in seismic data, there's a couple of key features we look for. First, you want to watch out for terminations of reflections, and you could kind of look for these in this example as I talk through them. So the termination of the reflections are our clearest indicators of a potential fault. You'll also see offset and stratigraphic markers, and you can see abrupt changes in dip. So other things to pay attention to are these changes in the seismic patterns. So sometimes seeing something kind of stop or change it's a signal that we should pay attention as an interpreter. You could also see fault plane reflections sometimes, and you may see an associated kind of folding or sagging feature around the area of your fault. So you got discontinuities in the data. And so in this example, we see a couple of these characteristics really clearly. And so I'm going to pause for a second and let you try to pick some of those out. Okay, I'm impatient. So now we're looking at the same data, but we've put on the interpretation overlay. And so you can notice now perhaps some of these features. Let me turn on my pointer. All right, so now that you've seen the result of some of the faults we've picked, let's go back. So here, if you can see where I'm highlighting it, here we've got that abrupt change in dip. So we don't necessarily have a offset or a discontinuity, a termination of reflections, but we see a change in dip. And we see that in a couple of places. We also see it over here a bit. So you'll notice that in these cases, the fault offset is not super huge. So you get that change in dip more than the complete termination. But down here, around this area of the fault, you do see that termination in reflections from the bright reflection and then into a more kind of transparent lower amplitude reflection. So we've got some folding and sagging that we're able to observe. And let me see, offset and stratigraphic markers. I don't see any clear indications of those right here. But so those are some of the ones you could pick out here. And we'll look at another example too. Okay, here's an example from the Hart textbook that shows both the uninterpreted and interpreted data for the same fault zone. I love these side-by-side comparisons because it lets you see what's being interpreted and then what it looks like in the original data. And so in this case, the interpretation points out a couple of key features: noise trains, which are associated with the fault zones, reflection offsets and terminations, and some subtle changes in dip. And so it's crucial to kind of understand these different expressions because faults won't always show up as those obvious breaks in the data, particularly in just looking at the seismic amplitude. Here's another example, again, showing an interpretation of another interpreter. We've got the uninterpreted data to the right of the interpreted data, and they point out some of their thought patterns of why they're calling this a a fault and what they're noticing. And I love this type of communication. It can be really good, particularly if for the reason you're interpreting seismic data is to a multidisciplinary group. So maybe you're working with engineers and drilling engineers, reservoir engineers, and you want to tell them why you see it's a fault. So in this case, I'll just read off a few of these. The first one, they notice an amplitude reduction in the fault zone, and they point it out. Yeah, we can see that. That's great communication. Let's see. Poorly organized apparent reflections. All right, so we've got that right in this area. This is where you have some of those weaker reflections, maybe right in this area. And when they're offset, it just kind of looks jumbly and noisy. And we saw that a couple examples ago too, in the highly faulted area. Here they point out a pseudo continuity of a straddle reflector. So right in here. And so they're showing, okay, it looks like this horizon continues across, but that's a pseudo continuity. Okay. And so they're pointing out a lot of the reasons they see faults, and even some of the features that may, like a continuation across from one side of the fault to the other. They're even pointing that out that, yeah, we see it's continuous, but we don't believe that that's actually the same lithology continuing on. So a great example of communication. I mentioned before the idea of tying loops, and so I'm just going to bring it up again. It's the same thing with horizons as it is with faults. So your fault must tie at intersection points. So when you're looking at a cross line and an inline or an arbitrary line that's intersecting another one, you want to make sure that the fault ties. And so I've got an example of what that looks like here. Okay, so now let's look at some more interpretation examples for different settings. So here's an example of a reverse fault. We're looking offshore Venezuela, and we see a series of very classic reverse faults that splay from a basal detachment. And so in the uninterpreted section on top, you can see the geometry, but then once you have the interpretation added in part B, the structural relationships become a lot clearer. And one of the things you'll also notice is that the faults splay upwards from that common detachment surface. And so this is a really typical pattern in compressional settings. I also want you to notice, even looking at the interpretation, how difficult it would be for us just to interpret this from this image, okay? To come up with a full interpretation like this, you're not often just looking at one line. You may be running seismic attributes, you may be looking at it in different directions. Here's an example of some flower structures. These are very distinctive features that we see often with strike-slip fault systems. And so we've got a couple of different types of flower structures shown in the figure on the left-hand side, from the synforms to the antiforms, and then another type of antiform, like a mixed one. And so in the seismic example, you could see how these faults kind of splay and resemble flower petals, hence the name. But so these are really good indicators of strike slip or transpressional deformation. All right, in terms of folds, we get folding in a lot of different environments. Some of the examples would be areas where we have excessive horizontal compressive stresses, in areas where we have shale or salt diapirs, differential compaction, arching due to intrusions. And so there's different characteristics we can look for in the seismic sections, from normal faulting and fractures that give us grabens at the top of the anticlines. We may have some signal deterioration below the anticline, and I'll show you an example of this. You may see that the folding disappears with depth sometimes, and you could see, depending on how you're looking at the data and what data you have, radial normal faults that are associated with the structures. We see these a lot around salt domes, and I'll try to remember to point them out as we look at salt examples. All right, so just a few reminders about folds geologically, because we want to make sure all of our interpretations are hinged in geology and what we know about it. So Folds in their simplest forms are bends or flexures in layered strata. So they can form in response to the fault movements and the diapiric movements or compaction that I just mentioned. And we can also, if our data is good enough, distinguish between forced folds, which are generated from forces below, or buckle folds that form more because of those compressive forces that are parallel to bedding. Just in terms of some more terminology, just to remind you what anticlines look like, synclines, and then also the hinge line and axial surface. So these are terms that I'll use a few times throughout the lecture. Okay, here's some very typical types of folding: the fault bend folding, fault propagation folding, and detachment folding. And we can see examples of those in interpreted seismic. So this is an example from offshore Borneo, where we can see the relationship between the folding and then also some of the faults that were picked in this more deep water fold belt. And so you've also got in here that you can notice the growth of the triangle zone that the fold thrust kind of creates. Very, very characteristic geometries. And one of the things you'll notice here, and it's not a great example for what I want to show you, but oftentimes around these folds, it can be very poorly imaged. Here's another example where we've got it uninterpreted and then interpreted. And so in this case, we could see a lovely fold. We can see some of those graben structures. It's a bit noisy, but we've got those at the top of the fold. And you could also see that signal deterioration right under it. So other things that I kind of mentioned before. And then here's another example, uninterpreted, from offshore Nigeria. And so what you see, hopefully, is kind of the broad folding pattern. And then once I lay in this interpretation, it becomes much clearer. And so what we've got in this area is, if we go back here, we've got these shearing zones that our eye can kind of pick out that disruptive pattern in there. But in terms of knowing how faulted it is, it's a little bit unclear for us to pick up. So again, something that the interpreters of this seismic probably had more information to help them determine it. This is a lovely figure that I show in a lot of my classes from offshore Namibia that shows a series of fault-related folds. And so you could see this really lovely regular spacing of them. So the regular spacing and how they're viewed kind of really suggests that these were probably formed under the same deformational kind of stress regime. All right, and then this one, I want you to, we've got a fault here, so you could think about this as kind of like an ungraded pop quiz. But we've got a listric normal fault in here. And so I want you to just take a minute to see if you can find that listric normal fault. All right, maybe just 10 seconds. And so this one, once we see it interpreted, it's much easier to pick out, but it was kind of hard to identify on the left-hand side. And so I throw this in here as like a good reminder to make sure that you're looking at, your data from multiple angles. So going through data sets in inlines or in cross lines may not be ideal for identifying the faults most easily. All right, and then another example, here we've got the Perdido fold belt in the Gulf of Mexico, so kind of on the western side of it. And you can see a really dramatic difference between the post-stack and the pre-stack time migration. So this pre-stack image over here gives us a much clearer picture of the steeply dipping west flank of the fold. And so this really demonstrates why processing decisions are so critical for structural interpretation. And if you can't remember the difference between post-stack and pre-stack, go back and listen to the lecture on processing, because those are really key terms to understand. And hopefully you understand when I said those words, why they look so different. Okay, so now let's talk about diapirs. So these are structures that form when we have salt or shale move through the subsurface, often because of density inversion or pressure or temperature differences. And so we get a lot of different features associated with them, and you could spend hours like going through all these features, so I'm going to do it really briefly. But some of the features you could see are evidence of flowage, withdrawal, collapse as the diapir moves through and then out of that area. You can have growth faults, normal faults, those flower structures, doming, piercement, compaction, detachment. So there's a lot of really fun features that you can see around diapirs, even that radial faulting. And so here's an example, a classic example from the salt of Mexico, the Gulf of Mexico, where we have a lot of salt-related structures. And so in this case, I just want you to see that there's a lot of different fault families that can be observed. From the ramp faults to the roller faults, you've kind of got those crustal faults. If we look at some salt in a few slides, you'll notice the radial faulting of them and toe thrusts. We've even got evidence of withdrawal in the system. And so those, of course, have to be marked out in your structural interpretation also. Here's another example from the Perdido Fold Belt, what I showed 2 slides ago, just showing how when we really zoom in and look at these, you have the larger scale faulting related to folds, but you could also have a lot of smaller scale faults, kind of shown by these keystone fault families that were picked out. All right, so I'm going to wrap up with my structural interpretation mini lecture. And just remind you of some of the key concepts. So with fault interpretation, you always want to remember to look for those signs like reflection terminations, offsets, changes, and dips. Those are kind of the big ones that you may notice. So it's also good to think about faults in terms of 3 dimensions and make sure that your interpretations tie at the line intersections. And if your fault framework doesn't make sense geometrically, it's probably wrong and you want to go back and look at it again. In terms of fold analysis, I showed a couple of different fold features from anticlines to synclines, forced folds, and the fault families that are related around them. You can often see associated crustal faulting, and one of the things you may want to pay attention to are different growth strata relationships in those folds. Again, just a reminder that processing is really important. So the more advanced processing that you're able to do will give you better structural results. Other things, of course, you want to integrate this with other data. So I always like to remind folks of that. So good interpretation shouldn't rely on just seismic data alone. You should put in the well logs or any information you have about the regional stress regimes through time in your area. And that's it for now. So thanks for listening.